We've all been there. You swallow a pill for a headache or some other ache, and you just trust that it's going to work. But have you ever really stopped to wonder how? Well, today, we're pulling back the curtain and taking a look at what is really going on inside our bodies after we take that pill.
Right? It's a great question. How does that little headache tablet know to ignore your knee and go straight to your head? It feels like some kind of magic, but it's not. It's actually the incredible science of pharmacology.
So the whole story of what happens with a medicine can be split into two main parts. You've got pharmacodynamics, which is all about what the drug does to your body, and then you have pharmacokinetics, which is what your body does to the drug. Think of it like a two-way street, and we're going to explore both sides.
All right, so let's start with that first piece of the puzzle, pharmacodynamics. This is where all the action happens. How does a drug actually, do something inside you? Okay, here is the most important thing to get right off the bat. Medicines are basically modifiers. They're not magicians. They can't give your cells brand new superpowers. What they do is work with what's already there. They either speed a process up, slow it down, or just block it entirely. A good example is an antacid. It doesn't invent a new way to handle stomach acid, it just chemically changes the acid that's already in your stomach. To really get how a drug can be so specific, we use this simple but really powerful analogy, the lock and key. It's the most common way drugs work, and honestly, it's kind of brilliant.
So picture this. Your body's cells are just covered in these tiny, uniquely shaped locks. In science speak, they're called receptors. Think of them like little docking stations, just waiting for the exact right molecule to come along and plug in.
Now, the drug molecule itself, that's our key. And if the drug's shape, its chemical structure, doesn't match the receptor shape, well, nothing happens. It's like trying to open your house with your car key. It just won't fit, it won't turn, and you get absolutely no response.
But when that drug molecule has exactly the right shape, it slides perfectly into that receptor lock. Click. That connection is what unlocks a specific job in the cell. It tells it to do something, like, hey, block that pain signal, or release this hormone. And just like that, the drug has found its target.
And this idea of a perfect fit is so important. Just like the quote says, the better the fit between the key and the lock, the less drug you actually need. It's like having a key that's cut so perfectly it turns the lock with almost no effort. That's what makes a medicine potent and super efficient.
Now, if we stick with this analogy, we can sort drugs into two main groups. First, you've got agonists. These are the keys that fit the lock and turn it on, causing a response. But then you have antagonists. These keys also fit the lock, but they just sit there. They jam it up, blocking any other key from getting in and preventing any response from happening at all.
Okay, so that's what the drug does to the body. But what about the other side of that coin? Let's follow the drug on its epic journey through the body. This is the science of pharmacokinetics, the incredible trip a medicine takes from the moment it's swallowed to the moment it's gone. So yeah, pharmacokinetics is the official name for it, and it's the study of what your body does to the drug. And lucky for us, there's a super handy acronym that breaks it down into 4 stages. ADMS. That stands for absorption, distribution, metabolism, and excretion.
So first up is A for absorption. The drug has to get from your stomach into your bloodstream. Next is D for distribution. Your circulatory system acts like a superhighway, carrying that drug to every nook and cranny of your body. Then comes M for metabolism. This is where your liver, the body's master chemical plant, starts breaking the drug down. And finally E for excretion, when your kidneys filter out the leftovers and it all leaves your body.
And this diagram gives you a fantastic bird's-eye view of that whole ADME journey. You can see the pill going in, getting absorbed, distributed by the blood, broken down by the liver, and finally kicked out. Pretty much every single medicine you take follows this exact same path.
So we know how drugs work and the journey they take. But let's be real, this process isn't always perfect. We have to talk about the other side of drug action, which of course includes risks and side effects.
This is such a core concept in medicine. There is no such thing as a perfectly safe drug. The very same substance that can heal you can also potentially harm you. And the one thing that separates a medicine from a poison is almost always just the dose.
So how do scientists actually measure that safety margin? They use something called the therapeutic index, or TI for short. It's really just a simple ratio that compares the dose that works with the dose that becomes toxic.
Here's a simple way to think about it. You have the effective dose, the amount you need to feel better, that's the ED50. Then you have the lethal dose, the amount that becomes harmful, the LD50. The therapeutic index is basically the size of the gap between those two numbers. A really safe drug has a huge gap. A riskier drug, well, that gap is a lot smaller.
Now, side effects usually fall into two big categories. You have the predictable ones, which are mostly dose-related. Basically, you took too much. But then you have unpredictable effects. These are things like allergic reactions, where your immune system freaks out, or something called idiosyncratic reactions, which are these really weird responses that are all down to a person's unique genetics.
So, when you put all of this together, what's the big takeaway? Well, it all comes down to finding the right balance.
This quote just nails it, doesn't it? The whole goal in medicine is to find and use drugs with a really high therapeutic index, the ones that give you the biggest possible safety net between helping and harming.
So at the end of the day, every decision to use a medicine is a calculation. It's all about weighing the potential good against the potential bad to find that sweet spot, that perfect therapeutic balance, where you get the most effective action with the absolute minimal risk.
And that leaves us with a really fascinating question to think about for the future. As we get smarter about all of this, are the next huge breakthroughs going to come from designing better drugs, these perfect keys? Or will they come from personalized medicine, from better understanding our own unique genetics, our individual locks? Definitely something to chew on.